Hey guys, welcome back. Today we're going to try to do a little bit of a virtual lab activity based on the information that we've learned so far about energy. So go ahead and take a couple minutes to write down the DRQ for today. We're on page 89, and then we'll go ahead and get started. Okay, so for today's information, we are going to be discussing the law of conservation of energy and how it ties to the topic of calorimetry. So the law of conservation of energy is one of those laws that again dictates the entire universe around us. We already learned about the law of conservation of matter that says that matter cannot be created or destroyed, only rearranged to form new things. Well, as it turns out, there's also a law of conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed, only transferred. So what that means again is that all of the energy that exists in the universe today has always existed in the universe. It just transfers between different objects. In terms of chemistry, we often think about energy as the energy of movement or heat energy. In the case of calorimetry, we're going to be focusing on heat energy, how the heat energy of one substance can transfer to another. And so we use the symbol Q to represent energy. So the law of conservation of energy really just means that Q out has to be equal to Q in. We see this happen all the time in our real life. Imagine that you put a very hot drink, like a hot tea or something, in the refrigerator. If you put a hot tea in the refrigerator overnight, you can eventually take it out and it feels cold. That's because the energy from the tea will transfer to the refrigerator. Hot transfers to cold. When we put an ice cube in a cup of hot tea, the heat energy from the tea transfers to the cube. The ice cube melts and the tea feels colder because hot energy or heat energy moves from hot to cold. Q out has to equal Q in. We're going to do a little activity today where we investigate how the energy of a metal can transfer to the water around it. If you remember the notes we did before, we looked at an example like this and we all agreed that the heat energy from the hot metal would transfer to the water around it and therefore increase the temperature of the water. So the Q of the metal has to equal the Q of the water. In an experiment, we use something called a calorimeter to determine just how much energy can transfer from that metal to the water. And based on that information, we can predict a lot of things about the world around us. Just how much energy each individual metal from the periodic table can transfer. As an example, let's take a look at aluminum. So if we take a piece of aluminum, and let's just imagine that that piece of aluminum weighs about 150 grams. Weighs about 50 grams. So in the lab area, we would do an experiment just like this. We'd take a piece of aluminum that weighs about 50 grams, and we'd raise its temperature to about 100 degrees Celsius. That's our starting metal. Now, then what we can use is something called a calorimeter. So this is a calorimeter. In a calorimeter, we add something like water, for example, and we'll add about 150 grams of water. And that water will be held at about 20 degrees Celsius. So our metal is here. It's very hot, 100 degrees Celsius. Our water's here. It's kind of cold, like room temperature. What we would like to know is how much energy will this metal transfer to this water? Now we know that the specific heat of water is 4.18. What we don't know is the specific heat of this aluminum metal. We can figure it out by figuring out just how we can change the temperature of this water. Just how much energy that hot piece of aluminum can transfer. So we'll go ahead and move that metal over. close up our calorimeter, and we'll wait and to see just how much energy can be transferred. When both the metal and the water are the same temperature, they will stop exchanging energy. So we'll wait to see that temperature stop changing, and when it does, we'll know that all of the heat energy from that metal was transferred to the water. Now, how does this really help us, though? Now we know how much we could change the temperature. So last class we learned an equation. Q is equal to mc delta T. In other words, we know that the amount of energy transferred from the metal is equal to the mass of the metal times the specific heat of the metal times how much that energy transfer made the temperature of the metal change. We can imagine that the energy of the metal will equal the energy of the water, then mc delta T is equal to the Q of the water. What that means is that if we take a bunch of lab data like we just collected for aluminum, we can determine that the mc delta T for metal has to be equal to the mc delta T for water. The temperature of the metal went down, but the temperature of the water went up. And by doing this, we can fill in all of what we know about from this data table and determine just what this missing piece, this specific heat of the metal, might be. So what I'd like you guys to do is use some algebra in this data table and go ahead and determine the specific heat for each of these three metals, aluminum, copper, and lead, using the data from this table and that equation at the bottom. Knowing that Q in has to be equal to Q out, then we know that the amount of energy absorbed by the water has to be equal to the amount of energy released from the metal, and therefore mc delta T for the metal has to be equal to mc delta T for the water. And therefore, we can use that equation to determine the specific heat of each individual metal. So you're going to do those three, and you're going to go ahead and write them in your notebook, take a picture, and upload them to Classroom. Hope to see you guys soon. Bye.